So it's a great pleasure for me to welcome Alan Willner to the University of Ottawa and NRC to the Schawlow-Townes Symposium. So I have some notes about him. So Alan is a professor in the Department of Electrical Engineering in University of USC, University of Southern California. He was the president of the Optical Society of America in 2016, so he's a major figure both scientifically, as you will hear, and in the management and administration of science. He got his Ph.D. at Columbia University. I looked this up in Wikipedia, and on his Wikipedia page, he's going to say more about it, it says he was supervised by Robert Boyd in Columbia. Now, I've sort of scratched my head about this because I didn't know Robert Boyd had supervised him. And I immediately asked Bob when I saw him today, and he said, no, nothing to do with me. But things are a little more cagey than that as far as I can tell. I don't really know anything more, but I do know that the Wikipedia page says he was supervised by Robert Boyd. So you'll have to stay and wait till the end of the talk, I think, and maybe he will tell us something about this, I don't know, this strange behavior. Anyway, we'll see. So after that, he went to work at AT&T Bell Labs and Bellcore. And so it wouldn't be too surprising that a lot of his work was on telecommunications after that. He's worked on signal impairment using nonlinearity, something that's deeply interesting, I think, to networks and how they work. Chromatic dispersion, polarization dispersion. The last time I heard him talk, which was just in June, it was on frequency combs and how they can be used in telecommunications. And well, we paired these. I know we sort of had a feeling what he might talk about. You heard Ibrahim Karimi talk about OEM beams, and I believe right now he's going to tell us about OEM beams and their use in telecommunications. But before he comes up, I wanted to just say that he's a member of the U.S. National Academy of Engineering, the Royal Academy of Engineering. I won't tell you everything. He was a presidential faculty fellow that was awarded by the White House, and he's the Eric Summers Award from the IEEE, amongst other awards. I just mentioned these. So welcome to Ottawa, and we look forward to your talk.
Thank you very much. Thank you so much. Let's see. Oh, perfect. So I will talk about orbital angular momentum beams, and Ibrahim, where's Ibrahim? So thank you for introducing a lot of that this morning. So, and I'll give a little bit of an introduction for those of you who may not have heard Ibrahim's wonderful talk. And I certainly want to thank both Bob and Paul for the wonderful invitation, as well as several other people who helped with the hospitality. Obviously, it's a wonderful celebration for Bob turning 70 years old. I have wonderful students and colleagues and generous support from various places. Only my students know how little I know. Right? I know so little about things. They teach me. It goes in one ear. It's sort of, there's a little bit of a buffer. It stays for as long as I can give a talk, and then it comes out the other side. But they were fearless. We entered this field of orbital angular momentum of light, not really knowing. Well, we knew very little. I knew nothing, and literally my students were fearless. They tried to do as much as they could. Whenever we wrote proposals, they said, let's try to do more. And so I really have just a wonderful group. Now, how many of you have, just by show of hands, have you heard the name Ibn al-Haytham? If you raise your hand. Oh, that's pretty good. In the US, it's even less. So for many of you, you know that the 2015 was the International Year of Light, and I never heard. I thought light started in the Renaissance, actually in Europe. Right? I didn't know it existed before. But so Ibn al-Haytham, the Saudi Arabian delegate to UNESCO, it was a 1,000-year anniversary of when one could say the first optical scientist. He published 7 volumes of optical science. I don't know if there's any nonlinear optics in there, Bob, but I don't know. Do you reference him? But anyway, I went over to him and I said, first I said I have a few students who are from Saudi Arabia. I said they have wonderful backgrounds, and I thought it was wonderful. And then I said to him, I've worked in this field for 30 years, and shame on me that I never heard the name Ibn al-Haytham. So there was a great celebration of him as well. I took a photo about a half hour ago of my tie. So for the Schawlow-Townes, I couldn't help. This was from Laserfest in 2010, and actually Professor Corkum also has an SPIE tie. So the ties are a thing of SPIE. So these are all these modes. These are the cavity modes of lasers. So I'm going to talk about modes. How can I not wear it? Okay, so I'm a great-grand student of Professor Townes. Charlie Townes. And for years, I didn't know this. And for years, I thought, I called him Charlie, right? So my advisor is Professor Richard Osgood. His advisor was Professor Javan, and his advisor was Professor Charlie Townes. I've been fortunate that several of my students have gone on. I have a great-grand student who's a professor in Malaysia. But so basically, many of you know Bob. Where's Bob? I can't see Bob. Bob. So Bob is a student. His advisor is Professor Townes. So so academically, where's Miles? Is Miles here? I'm next to Bob's my uncle. Thank you. Those of you. Okay, very good. Well, this is the Wikipedia page that Paul mentioned. And it's very funny because, that's my Wikipedia page. Somehow I went to, it says my academic advisor is Robert Boyd. Of course, people also search for, I guess it was pasta. I guess Miles is holding some pasta there. So again, this is sort of a community that we really populate together. Of course, here's Bob and Miles. But I know, first, I didn't create this, and it's not right. Right? It's wrong. My advisor was Professor Osgood. But the people who did it, the reason, so I don't correct it. I never corrected it for a very simple reason. I wear it as a badge of honor. I didn't create, so I didn't make the mistake. But whoever did it for a reason. And that's because the mistake they made was because they know how much I talk about Bob, how I feel about Bob, and how I look up to him. And they assumed he was my advisor. For good reason. For good reason. And Bob put it up, right? Yeah, that's right. So this was, if you want to know a person, this is probably the best photo that I have to really give you the essence of a person. So Bob, in the same year, he won the Schawlow Award and he won the Townes Award from the APS and OSA respectively. And of course, Charlie Townes was his advisor, Professor Townes. So Professor Townes had already passed away. This photo, I wrote, as Paul mentioned, I was the president of OSA, so I had 12 of these president's messages. And I only had one photo that I put up in the messages, 1 month, and it was basically about, this photo because it was a gem, it was priceless. Because he wanted to show tremendous respect and warmth and honor to the Towneses. Professor Townes had passed away, so Mrs. Townes, who I think was about to turn 100 or had just turned 100, I forget. Just turned 100. So she was the same age as the OSA. The OSA was the 100th anniversary then. And you should have seen it. You can't make, so Bob they had arranged a crane so that she could come onto the stage. And this photo was just priceless, right? That Bob was giving honor to Mrs. Townes to Professor Townes. Now, I'm going to talk about optical communications. And the thing about the Schawlow-Townes, the idea of using lasers for optical communications wasn't dreamt up later. So this goes back to the patent for masers and maser communications. So they talked about using lasers for generating monochromatic radiation, modulating that, and so on. So the idea of a generator of the coherent beam, modulating it and detecting it, this is the patent that was from, I believe, 1960. Okay, so they knew early on, and it's amazing how much foresight that they had. Now, this is my last introductory slide, but just for those of us who've been in optics for a long time, there's how useful optics would be is always the question, right? You work on the research end of it, and you think hopefully there'll be an application. So it was clear that long-distance communication would be optical fibers because of low loss and high bandwidth. But what nobody could predict was something like this. So because of climate change, there was, if you want to go from the Pacific Rim and trade in Great Britain to do like stock trades, normally you would just go to the west coast of North America and then retransmit from the east coast. But if you what they did was in late 2014, they laid a cable over the Northwest Passage over North America. By so doing, they saved a grand total of 24 milliseconds just because of the speed of light. Now, they spent $850 million. So they spent on the order of 30-something million dollars just to save each millisecond. Because as we know now, each millisecond means big dollars when you have sort of rapid trading. And who would have predicted that that was now one of the drivers for somebody spending $1 billion? Okay, now for OAM, this just gives you an idea. OAM, this orbital angular momentum, one could say, and again, there are people here who know much more than I do, but the number of papers published, if you just go to Google, is now several thousand. It's growing and growing. This part here, the small one, is the number that talk about optical communications, so that's growing. My students were very fortunate to be involved in something that's young and growing. I just had a fun. I was going to try to figure out how many of these actually reference Miles and Bob. If you, that would. It's like I would go over to them and say, "Why didn't you reference it?" Okay. So again, I'm not going to go through. I have just a couple slides on introduction for those of you who aren't here. But different than spin angular momentum or polarization, the polarization of light. So you can have linear polarization. This is taken, of course, from a wonderful paper, Advances in Optics and Photonics, from Miles's group. And so you have two polarization states of light, whether it be linear or linearly polarized or circularly polarized. The thing about communications is you want orthogonality. Orthogonality means if I have two orthogonal states, I can put information data on one state, and in an orthogonal state, I can put a completely different beam of light, a different data stream, and then I double my capacity. If they're orthogonal to each other, I can combine them with little crosstalk, I can propagate them with little crosstalk, and I can separate them with little crosstalk. So the whole point of orthogonality, again, it's like frequency multiplexing in the radio world, right? All I need is a filter to be able to separate things out and have minimal crosstalk. So that's in polarization. All you've got is two states. With OAM, you have potentially many more states. So in this case, this just gives orbital angular momentum. This is the case where L equals 0, L equal 1, L equal 2, L equal 3. And so this shows the intensity and the phase. The intensity, if you have a plane wave, where if you cut the beam, if the entire beam is just oscillating up and down together, so you have a beam of light, and the spatial structure of the phase front, if it's just propagating and it's going up and down like this, then there's no change in the phase. However, you could have a case where there's orbital angular momentum being carried by the beam where the phase is not oscillating up and down together. So if you have a beam of light, you could have it so that the different parts of the beam are doing this. And then the phase is not the same. Depending upon how this twisted light is propagating, it could twist slowly, it could twist faster or even faster. So again, the phase front is doing a helical twisting as it propagates. Once it has this helical twisting, it becomes a donut in the intensity. And in phase, if you cut the beam, you would see a 2 pi phase change in the azimuthal direction around a circle. That's if L equals 1. If L equals 2, it's 4 pi. L equals 3, 6 pi, and so on. This is like a Fourier series. So a Fourier series, you have cosine omega t plus cosine 2 omega t plus cosine 3 omega t. You have lots of terms. They're all orthogonal to each other in the series. Well, the same thing is true here. Each of these, this is e to the IL phi, each of these would be orthogonal to each other. So if I put a gigabit per second on this beam, a gigabit per second on this one, and this one, I put them together, I have 4 gigabits per second. So it's a force multiplier in a communication scheme. It's a fairly straightforward process. Like, it's straightforward in hindsight, but at the time I'm sure it was, it wasn't clear. You can use a phase hologram, a spiral phase plate, spatial light modulator. There's lots of different techniques to use where you take a plane wave and you can create this OAM beam if you put it through a phase hologram, so you can impose on it a certain amount of OAM. At the receiver side, if you want to try to couple it back to, let's say, a fiber or some sort of a detector, it's quite often convenient to take this OAM beam and have it go through a reverse phase function, convert it back down to the fundamental Gaussian, and then recover it. So this gives you the idea, and by the way, I should say, I'm not going to talk about OAM and fibers, although that's a completely, that also is fairly vibrant, but I'm going to stick to free space for this talk. So back at the time of Marconi, 100 years ago, you have an aperture pair. You have a transmitter and a receiver, one aperture pair, one beam. Several decades later, they had polarization multiplexing. They had a beam on one polarization, orthogonal beam on another. They had twice the capacity. But with OAM, which is different than polarization, you could put a bunch of beams that are orthogonal on one polarization, a bunch of beams that are orthogonal on the orthogonal polarization, and now you have twice as many, well, you have 2 times the polarizations, and you have n times the capacity. And so one could do this, and it's been demonstrated up to many different simultaneous beams. And by the way, you could, this helical twisting could be clockwise or counterclockwise, and I think that was alluded to before. So you could twist clockwise or counterclockwise the phase front, and you get a factor of 2 there as well because they're orthogonal. This just shows you the sort of exquisite way of spatially structuring the beam. In this case, you have optical transmitters, you have a beam of light, but then you can twist the different beams with different amounts of twist. You can combine them and then separate them at the receiver. And this just shows you interferograms for four different modes. This is a +4 value, +8, -8, and +16. So you can see these spirals. The interferograms are interference between an OAM beam and a regular Gaussian, and that's where you get these spirals from. But you can see that there's, for a +4 value, you have four different light and dark, 4 different 2 pi phase shifts. Again, the idea at the transmitter is you take your Gaussian beams, put it through different phase holograms. You combine them all together so you can't spatially separate them. They're all overlapping. They're all donuts, right? But if you can detect them at the receiver. And I'll mention that now. So here is, just as an example, these are 4 different modes, -8, 10, 12, -14. This is them all together. As you see, you can't separate them. But they are all orthogonal, and each one of these is carrying data, carrying information. Now, what is unique, so when you have a radio, in your radio, what do? You have a filter. You tune a filter so that only one radio station in the frequency domain, only one radio station passes through. So here you could use a spatial filter as an example. You could also use a Glasgow mode sorter, an Ottawa-Rochester mode sorter, various other mode sorters as well, but this is a simple case. If you convert these, if one of them converts down to the fundamental Gaussian of 0, that goes into the center. So if you put a phase hologram of +8 on the receiver, you get this becomes +8 and -8 is 0. That comes into the center. something else happens. So plus 8 is plus 18, plus 20, minus 6. So you can see here, there's the one you want is in the center, and the other ones are crosstalk around, and I can put a spatial filter. But again, there are mode sorters which allow you to recover all of the modes at the same time. And I refer you to that wonderful work. So in terms of communications, how many folks here are familiar with quadrature amplitude modulation? Okay, so again, I'll just keep this quick and simple. A wave, an optical wave, cosine omega t plus phi. It's an optical wave. It's a vector, right? Cosine is a vector. A vector has magnitude and direction. So what you have is magnitude and phase, right? So here in on-off keying, where I just blink light on and off, I can represent it in a constellation where I have a real axis and an imaginary axis, I and Q, right, in phase and quadrature phase. So in the case of just on and off, my vector points to the right with 0 phase and some magnitude. If it's 0, it's right at the center. That's all I see. I see 2 dots if I look at the constellation of information. Now, if I have phase shift keying, I can change the phase of the wave by pi. So here the phase of the wave changes by pi when I go from a 0 to a 1. And from a 1 to a 0, I put another pi phase shift. So my vector of the beam goes, instead of from the right, it goes around the circle to the left. So I have plus 1 and minus 1 instead of 1 and 0. And that gives me, one of the nice things about it is, as you can see, I have a bigger effective signal because I'm sending power, energy, in my 0 bits. And Shannon tells you that energy is information. So this gives me more of an effective signal. And in terms of quadrature amplitude modulation, this vector here can point to any direction and amplitude. So in this case, I'm showing 16 possibilities for the vector. And so in one symbol time, I have 16 possibilities, which when you think about, let's say, bits of resolution, it's 2 to the 4. 2 to the 4 is equal to 16. So it's 4 bits of resolution I'm sending in a single bit time. So it's very spectrally efficient. It's very efficient in terms of the spectrum that you have. Okay, so that's just background. And this just shows you 16 QAM, quadrature amplitude modulation, of an OAM beam that's by itself. And when I turn on the other OAM beams, it looks pretty much the same. There's very little inherent crosstalk because you've structured the beam so that they're orthogonal, which means you can easily, or not easily, but one can put them together, propagate them together, separate them with minimal crosstalk. As I mentioned before, polarization, it's compatible with polarization. It's another multiplier, another domain, as you will. It's also compatible with wavelength multiplexing. So many of you are familiar with wavelength multiplexing in fibers and free space. But this is just another domain, and you just add it on. So in this case, these are 42 wavelengths. Each of these wavelengths, my students put on 24 independent data channels. So 24 modes, 24 channels times 42. They did over 1 meter in the lab. They sent 100 terabits per second. And they measured 1,008 bit error rate measurements to show that it was working. And so this was in the lab in 1 meter. And I could say that it was 1,000 millimeters to make it more impressive. But it was impressive. It was impressive. But some of the reviewers, of course, I started learning this much later. There's nothing like a challenging review on a paper. So this was published, but there's nothing like a challenging review to motivate a student, right? It's like a flag. It's like I don't think this will work outside. I don't think this will work beyond a meter. So what did they do? They said, I'm going to show the reviewer. So the next paper, it was published, but the next paper, they went up to the roof and they propagated 120 meters. And they just did it. They did no signal processing, no adaptive optics. They went up to the roof of the building and they did about half a terabit, because it was hard to get all the equipment up there. It's a good thing it doesn't rain much in Southern California. Anyway, could have been an expensive project. So they propagated 120 meters, and it worked. It worked because there's not much going on. So they published that, and then there was, people questioned, okay, well, that's nice, but what if you really had turbulence, atmospheric turbulence? So that became a key issue. I'll get to that in a minute. I want to back up. Some of you may have heard about it. There was this one question that kept on coming up, and Bob and I had many discussions, Miles and I had discussions. Why are we're talking about this orbital angular momentum, but there are many different orthogonal modal sets, right? So you could have Laguerre-Gaussian modes. A subset of them have OAM. You can have Hermite-Gaussian, linearly polarized vector modes. You can have lots of different sets. In reality, sort of each set it can be represented by other sets, right? So it's just how you define them. So the question is why? Why use OAM? Number one is we did it, right? I mean, and many people did it. And one of the reasons is so you could do it with other modes. God bless you. Go ahead, right? It's fine. One of the nice things about OAM is that it's round. So it has circular symmetry, and lenses tend to be round, right? Optical telescope, things tend to be round, and it's convenient. But in theory, you could, there are some engineering issues, but again, you could do it with an orthogonal modal set. But, again, that being said, my students were like, they got these reviews, and they said, oh, gee, other modal sets, whatever. So they did it, and they published it. It just came out this year. But they said, okay, let's do it with Hermite-Gaussian modes. They did it with LG, higher order LG modes, and they did it, and they sent hundreds of gigabits per second. As I said, I should write reviews for my students, but they're not anonymous. That's the problem. Oh, I don't. So anyway, there was a kerfuffle, right? Kerfuffle, which I had to look up. A kerfuffle about OAM, which was I don't know how it started, and I don't really know how it ended. But there was I think the BBC got a hold of it. Nature was sort of the people there were engineers and physicists. Again, I think it's a rough boundary. That people who were doing MIMO radio, right? So multiple input, multiple output. Many of you are familiar with that. Multiple antennas at the transmitter, multiple antennas at the receiver. They said, well, OAM, where you transmit a bunch of modes, is nothing more than just spatial multiplexing. It's like MIMO. And then there was back and forth. I won't recount it. But at the end of the day, fundamentally, that's true, right? OAM is spatial multiplexing. It's mode multiplexing, a subset of spatial multiplexing. You've got a bunch of beams. But practically, almost on an engineering level, how do you deal with crosstalk? And that becomes sort of one of the key differentiators. In MIMO, in the radio world, the way that they deal with crosstalk is they embrace crosstalk, right? You transmit from a transmitter, many receivers recover it, right? And you have all this crosstalk, and then you use MIMO digital signal processing in the electronics to unwind the crosstalk. With OAM, you inherently structure the beams so that there should be little inherent crosstalk to start with. So hopefully you should not need as much or hopefully minimal digital signal processing to unwind the crosstalk. Okay, now what if you have crosstalk? And crosstalk will come about for many reasons. One of the obvious ones is turbulence. So if you have this wonderful mode here, if you have turbulence, there could be changes in the index of refraction of air. When you change the index of refraction, you change the speed of light through it. There's a phase change. If you change the phase of a beam, you no longer have this beautiful phase structure of OAM. What will happen is there'll be modal power coupling. So the mode starts to look like this, and power is coupled into other modes. So what do? So one thing you could do is use adaptive optics. And it's basically similar to what people do with adaptive optics, right? You basically have turbulence here. It takes the OAM beam and it messes it up. And then hopefully you can undo the turbulence of of the medium. And the way that can work is to simply use a spatial light modulator and by a feedback loop and measuring the wavefront to give at the receiver an inverse function, an inverse phase function that happened in the atmosphere itself. And hopefully you can recover it. And what was interesting was that you can do it, right? So to first order, that here's your OAM beams, 1, 3, 5, 7, 9, they're all together. And if you put a phase function that undoes, hopefully, the atmospheric turbulence, to first order, they all come back. Now, there's still a little bit of penalty, but to first order, you can undo it with adaptive optics. What about MIMO? So it's kind of like, again, the folks said MIMO signal processing is, it's nothing but MIMO. Well, they're right? Let's embrace the MIMO-ness, right? MIMO-ness, I don't know if that's a word. Okay, here's your bunch of beams, they're messed up. So if I have distorted OAM beams, it looks like there are multiple antennas, multiple receivers, and they're coupling to each other, cross-coupling. I can use DSP in the receiver to try to undo it. And this is the result. It works the way it's supposed to. Here's a bunch of beams. Here's the data constellations. Channel 4 is really messed up. But after putting it through digital signal processing, it comes back. So you can unwind the crosstalk in a similar way than you could in the radio world and also using adaptive optics. Now, I believe this was mentioned before. I think it was in the Q&A with Ibrahim. So Anton Zeilinger's group in Vienna has done wonderful work. I loved this work. What they did was they sent a beam of light between the Canary Islands here, over 140 kilometers, and the beam of light had a certain phase structure. And at the end, using some digital signal processing, they were able to recover the phase. So again, when people were saying, oh, this wouldn't propagate, it did propagate, and it was able to be recovered. Now, the Zeilinger group is not a communications group, so I think this was on the order of bits per second, or maybe kilobits. I think it was bits per second, but it was astounding. And we do communications, so we upped the bit rate. But this was published, and again, it was mentioned this morning. So again, my students, oh yeah, it'll work if on stationary, but it'll never fly. So my students said, we want to fly a drone. We got funded from the Air Force. They had this BAA about to communicate with an airplane that would at at Mach 1. And we eventually did this drone. We got funded. The drone flew, as you'll see, at 0.1 meters per second. So we got funded, but so it was interesting to them enough that they backed off of their spec by several orders of magnitude. Anyway, so they bought a drone, and they wanted to fly and transmit between the drone. And it was roughly around the time Amazon was talking about delivering packages with drones. Okay, so what they did was, this was 50 meters, and they put a retroreflector up here, so it was 100 meters back and forth. And they took it off, they hovered, and they had to propagate at 0.1 meters per second. I want to mention, pointing and tracking is important. If you don't, this is harder than a regular beam, which, again, take a negative into a positive. It's harder to recover, but it's also harder to eavesdrop. So it's, in many ways, it has a lower probability of intercept, a lower probability of detection by someone else. So what happens is it'd be nice if you recover the beam by your aperture, but if your aperture doesn't recover the beam on center, you have a problem. What happens is you're not recovering what the phase is, the phase change of your beam. Let's look over here for a second. So if you're not directly on center, let's assume I have an aperture. Here's my phase change. If my aperture is in the center, I see in this case a 4 pi phase change. But if my aperture is over here, I don't see much of a phase change. It's kind of like it's like a frequency filter that has like an infinitely large full width half maximum. You don't know what frequency you're at. You don't know what phase you're at if you're not in the center. So number one is it would be nice to be in the center. You have the biggest phase change. The second problem is that in the center of your vortex, you have very little power. So you need to get you know what it is, but you can't measure it. So you need to have enough of an area so that you can recover enough signal, but then also be in the center so that you can minimize the crosstalk. And so you need to have a feedback loop, and that's what my students built. They built a feedback loop so it was able to stay centered. I will say that they got their pilot's licenses to fly. It's very delicate. I went outside. I wanted to fly it. So they really were nervous. They did not want me to touch it. But you know, they're like standing to the right and left of me, and I got it off the ground about this far. No, okay. It's like their future was in. Okay, so this is when this is locus of dots hitting the detector when it was on the ground and the rotors were going. This is when it was hovering, and this is when it was moving. And what you really see is that it's trying to do the right thing with the feedback loop. And you can buy feedback loops that are really great. And this is just students doing a wonderful job, but as you can see, it still worked. Over the course of a minute, as it was moving around, sometimes, most of the time it had no errors. But if there was a gust of wind, because the feedback loop was built just by hand, sometimes you would get some more errors here and here. This is the bit error rate. What about underwater? So again, the idea that you can do things underwater, right? One of the nice things about underwater is you're not going to travel that far. So in the blue-green, there's a lot of interest right now, right? In the blue-green, which has lower losses than in the infrared, that could you increase your capacity, but these OAM beams that are how delicate are they? How can they propagate underwater? And this is some results here. So here's tap water. This is in a fish. I guess there were no fish. That would have been an obstruction, actually. So if you ever see a fish with a big donut hole in it, you'll know it's, oh God. Anyway, water currents, Malox, and turbulence. So water currents, it turns out, does nothing. Right? Just flowing a pump water doesn't do anything. Malox is used not only in your stomach. I learned that Malox replicates the turbidity, the scattering and loss of water, of ocean water. And then turbulence, which is a temperature gradient. So as you can see on the right, the OAM beam, it's the turbulence that gets you. It's the temperature gradient. And that makes sense. Again, in hindsight, it makes sense because a temperature gradient changes the index of refraction of the water, which changes the speed of the light, which changes the phase front, the relative phase front. And it's pretty clear that would be the big problem. We did 4 beams at 10 gigabits per second, so that's 40 gigabits per second. So I'm going to skip through this because I want to do the quantum and then I'll finish. So quantum, it was the only reason I did quantum is because of Bob, right? Bob was he had been doing OAM in quantum, and it was just we collaborated in the past. Bob is a master collaborator. He is selfless. He shares credit. He is wonderful. He is exciting. My students love to talk to him. They love working with him. His enthusiasm, there is no half-life to Bob's enthusiasm for the work and for the people he works with. So this is what he did. It was shown before, way back when, it was shown early on that a photon can carry OAM. This is a recent publication actually showing, I guess this is a collection of photons, but it's very low light level that it does have this structure. So that came out very recently. But the idea in a quantum system was that you would encode, not multiplex multiple beams. Have one, there's no beam, there's one photon. But encode it on OAM states. So normally when you think of quantum, you think of, if you're using polarization, you use one polarization state or the other for the 1 and the 0 qubits. Okay? With OAM, as we've talked about, you have larger number of states. So in this case, so what you could do is every photon here can be placed on another OAM state. So if I have 7 OAM states, I have now a more powerful quantum information system, right? I have a larger alphabet to use. And I chose 7 because that's what Bob published. Mohammad Mir Hosseini, he actually combined angular states with OAM states, but I'll focus just on the OAM. He encoded each photon was either on one of these 7. And that gives you a larger alphabet to work with. And so these were it was from -3 to +3. And what we did is we took that concept and went a little further, where we took these OAM photons, right? Each photon is now on a different state. And we combined it with a Gaussian beam. So a classical beam. It could be a beacon beam. It could have data on it. But basically what the community now calls coexistence, that you have a quantum channel along with a classical channel. This is going to be tiny compared to the Gaussian beam. So can you send them together? And the answer is you can, right? That you can, as long as you have filters and separators and so on, you just use your space. And if you put one on a wavelength far enough away, on an orthogonal polarization, whatever, you can separate out the classical channel. This shows you at the transmitter the L equals -1, L equals +1, and the combined states. This is using a quantum detector. So this is the hits in your detector on the one state, on one of the OAM states, hits on the other OAM states. This is at 10 megabits per second. And this just shows you the quantum symbol error rate as a function of the photons per pulse. What you see here is that there's more of a penalty. This one here is a higher penalty as opposed to the lower ones, because this one here, the modes are very close to each other. You need to separate modes. In the future, there'll be better devices to do that. But if you're, just like wavelengths, you do better if you separate your wavelengths very far apart, if you have a filter. The same thing is here. When you separate them by like 3 modes apart, then it's lower. What my students did at Tong, she just was published at Clio. She used adaptive optics. So the question was, and we were at a review in ONR, and I didn't realize that people were very interested, right? Adaptive optics has been used, and Bob has published this as well, that can you use adaptive optics to undo the turbulence for a quantum channel? And this just shows some of the results. The quantum symbol error rate. This one here is the back-to-back. Up here is where you have turbulence. We emulated turbulence in the lab. And this here is where you turn on the adaptive optics system that I showed you before. So as you can see, the penalty dropped close to the back-to-back case. It was able to do a fairly good job. I won't go through it, but this is, so the Schawlow-Townes, Professor Townes, I hear knew something about masers, and M stands for microwave. So we also did OAM in microwave. And just tell the students, Intel had put out they wanted to fund OAM in the microwave, in millimeter waves. They cited our paper in optics. I knew nothing about microwaves or millimeter waves, but they cited our paper. So I had to put in a proposal. Right? So we got funded to do it. And it's from the physics, the proofs of concept of physics, it's pretty much the same except for how you do it. You can put it through, these are spiral phase plates, again, some lovely original work from Miles's group, where depending upon the height offset of a spiral phase plate, you can induce in the millimeter wave, the microwave, L equals 1 or L equals 3. This is what it looks like. This is the Teflon, basically like a Teflon structure. and they're big, so you can see it. You can take a picture of it. This is the antenna. And this just shows the result. Again, it's the same principles, right? Here's your amplitude, and here's your phase. This was plus and minus 1, plus and minus 3, and you were able to multiply the amount of capacity you have in your system. I want to make a comment that the first talk I was hired by Ivan Kamenow at Bell Labs. He passed away a few years ago. Wonderful man, pioneer. The first talk, he was talking about these in the late 80s, was talking about gigabit networks. So somebody raised their hand and they asked him, what are you going to use gigabit networks? So this was in '88 when people were using telephones and iPhone minus 100. I don't know, whatever it is. So what are you going to use gigabit networks for? So he said, well, when they first invented paper, they thought that they would print the Bible on it. But then we end up using it to wrap fish with it. He says, I don't know what we're going to use gigabit networks for, but it probably will be useful for something. And I think there's a lot, we're learning, this community, it's so interesting. There's physics and engineering, there are advances going on at an amazing pace by the whole community. And again, I give credit to the pioneers of the community who really embraced it to grow, that there's a lot to be learned and a lot of exciting things in the future. But, of course, to Bob, right? He is 70 years young. Warmest congratulations. And you're an inspiration to everyone. And I say your friends and admirers because all of your friends are your admirers. So congratulations.
Hi. So what causes the physical limitations of the number of polarizations?
Oh, polarizations.
Yeah, and
the physical limit.
And what is that number?
And what is it? What is the definition of a politician? Somebody who answers a different question that was asked? One of the things, one of the first questions I was asked when I first got into the field was, how many modes can you have in it? A lot of people say that in theory there are an infinite number of OAM modes you could have. And so one of the things is, if you notice that the mode size grows larger as you go to higher order modes. And so in theory, if you wanted an infinite number of modes, you need an infinitely large aperture, which doesn't exist. That's one of those fundamental limitations. It's very much like the wavelength space, right? In most systems, you have a wavelength spectrum that you have to deal with within that, and that's kind of like your aperture. Now, your question is about polarization. I'm just looking around. Probably half the people in this room know more about polarization than I do. Does anybody want to take a crack at that? Maybe Paul? So I don't know what fundamentally limits it to 2.
So thank you for a lovely talk, Alan, and your kind comments. I've just got 2 things to comment on. And of course, the kerfuffle, was that the word you used? Yeah. And the discussion whether essentially modes being separate fundamentally from birth or whatever, like OAM, to what extent is that equivalent to the separation that one can post-apply through a digital signal processor? And in defense of OAM, I would say digital signal processing works very well when you've got many photons per measurement. But when you've got 1 photon per measurement, I don't think you can do digital signal processing to separate your channels. What you would then have to do is build an interferometer. Your digital signal processor would have to be a network of waveguides or whatever. So I think, and what I want to do is agree with you that keeping the modes separate in the first place is better than trying to unscramble them digitally after you've measured them. So I think that's true. I'm be interested to see whether people disagree.
I love that. I love that. No, because you're right. I mean, you need to know something about the field.
So let's pretend
you lose that in the electronics.
Exactly. The other thing.
It's wonderful.
Was that you were asking about, how many channels can one transmit? And I think the answer is, in terms of low loss transmission, the answer is always the Fresnel number of the optical system. And that doesn't matter whether they're OAM modes or whatever modes. It's the Fresnel number of the optical system tells you the number of low loss modes. However, OAM modes, I think, have another interesting property in that if you stay aligned, and you talked about the importance of staying aligned, and if your aperture's too small, then sure, you have loss, but the modes are still orthogonal. And often in a communication system, it's not the loss that kills you, it's the loss of orthogonality that undermines you. And so the fact that no matter how small your aperture is, you may lose horrendous amounts of power, but if you stay aligned, you are always orthogonal. And I think that's another advantage that these modes might have.
So everything you said about the alignment remaining, everything we've ever measured or simulated follows exactly what you said. As long as you're in the center and you have that full phase change, the crosstalk is inherently not there. So yes, that's wonderful.
So I just want to go in the same direction of discussion. So I agree with Miles that Fresnel number really dictates how many modes can you send. And if you want to make a competition between OM modes and multi-spots Gaussian beam, definitely multi-spot Gaussian beam will win unless you want to include P number. If you include P and L, then you are in the Schmidt basis, and I think that dictates what's the maximum efficiency that you may have in the specific numerical operation in your system. So
yes.
I thought that's important to be shared.
And so yes, the LG modes have L and P, the two indices that define the mode, and one can have all the P modes, L modes, and the combinations thereof. And yes, exactly. With the various engineering issues that will go along with recovering them.
This is clearly the OAM role here. So I'm not sure if I should say thank you or not for embarrassing me so badly, but in any case, I think thank you. But I had one technical question. You said something that just struck me. You said that when you go from on-off keying to 16 QAM keying, there is no penalty in the bandwidth. Let's go with the electrical bandwidth of the transmission system. And in some ways I see it, and in some ways I don't. So is that literally true, or is it just almost true?
So, right. So if you were to, let's say in the time domain, you can go on and off, right? But it's like an M-ary system. So M levels, right? So you can have 1, or I can go up to 2, or up to 16. And inherently, sort of, when you define sort of this time period, and then the frequency you need is roughly 1 over the time period, they're kind of the same. So you're fitting more potential levels and information in the same bandwidth. So you're, in that regard, now, what about if I went to 1,000 levels? The answer is then I need, just to sort of take your question even further, it doesn't come for free. It means I need to have a much higher either signal power, but I have a certain noise in my system. So to keep the same signal to noise ratio, I either have to increase the signal or reduce the noise. Because I need those dots, I need to separate them. And in a fiber, let's say a fiber, not free space, you're limited by nonlinearity. So you can't just continue to increase your power. So the answer is, the bandwidth is kind of the same, but you have a higher requirement on the signal to noise ratio. So it's an excellent question. Thank you.
Join me, please, in thanking.